Well, we're going to have a look at some chemistry. We're going to have a look at the periodic table, and we're going to have a look at basically its development. And then we'll have a look at some reactions. Now, development of the periodic table's taken place over many hundred years. Basically, people saw different types of elements, and they tried to work out, well, was there a pattern? For a long time, elements had peculiar symbols, and you can see these next to the picture of John Dalton. They had sort of patterns, and they started working out there was difference in these elements, and we started looking at their different sort of masses. So we looked at them in the forms of their atomic mass or atomic weight. Funny symbols used then, and it made life quite difficult to try and sort of work with. So various people looked at different ideas. In England, a gentleman called John Newlands had a go at his law of octaves, and he tried to make a little pattern, but many of his critics said, well, he'd have done just as well on his patterns if he'd sort of put them in alphabetical order. So that didn't really get on very well. He did manage some really quite good ideas, really. He was on the right idea, on the right lines. There have been lots of other scientists did a lot of other work, but their work really wasn't well published and well documented until this other gentleman, Dmitri Mendeleev, came along, and he used that same type of pattern, but he left gaps. And it was this idea of leaving gaps. He wasn't the first to come across this idea, but his was probably the most publicized and the most well received. And so we have all these different ideas about how we can link our elements together to make these sort of repeating patterns. Some of the ideas of how we can produce periodic tables are rather unique. This is one published by abundance, so we can see which elements are the most abundant. And later in the course, you find that we worry about some of these because we are fast running out of some of these elements. They're becoming much, much harder to find. These are elements found in and used in a smartphone. And you can see that hydrogen, carbon, oxygen, plenty of magnesium, aluminium, silicon, yeah. But getting further down the list, the periodic elements become more difficult to find, and they get more rare. And perhaps in a few years' time, we're going to have some problems trying to find some of these. We've got some of them highlighted there in orange and in red, and those we're going to find difficult to get hold of. So when Mendeleev started his periodic table, we actually knew quite a few elements. As you can see at the end, we didn't know about any of the noble gases, and we had holes. Scandium hadn't been found. Gallium, germanium hadn't been found. Fluorine, very reactive, hadn't been found. And so he built his periodic table with holes in so that we could try and find these elements. Now, if we want to look at our periodic table, we look at this in a special way. We've got items going down. These are called groups. And all the elements in these groups share, as we're going to see in a few moments, similar properties. So the group ones share very similar properties. The group two share similar properties. Going across, we call them periods. And on this periodic table, we have the elements changing. We have first the group 1s, then the 2s, 3s, and they start getting more electrons in their outer shell. Well, so much for having a look at the periodic table. Let's have a look at the actual elements to see what we can make of these. So the first set we're going to have a look at is that of the alkali metals. And we've got a picture of some of those, but I'm going to get some out so we can have a look at them. Important things to think about before we start, that they're all low melting points and boiling points. They're all soft, they're all very reactive, and they all need to be stored under oil. They react pretty violently with water, as we're going to see, and we'll have a look at them. Okay, so let's see what we can do by having a look at these particular elements. Now, what I want to do is I want to basically look at some of the properties. So some of these properties we're going to have a look at basically consist of the reactions with water. So I'm going to look at lithium, I'm going to look at sodium, and I'm going to look at potassium. And what we're going to do is we're going to have a look at their reactions with water. We could go on down the periodic table and have a look at other elements, rubidium and cesium. Now, I'm not going to look at these particular two elements because basically I can't afford them. Rubidium comes in at around about £100 a gram, cesium slightly more, and it's an expensive experiment to try and do that. So no, I'm not going to try rubidium. I have used it once in the past and it is quite dangerous, and I'll be honest, I've never actually handled cesium, although I do have a small sample of it. Right, let's have a look at lithium, sodium, potassium, and we'll make predictions for rubidium and cesium. The setup that we've got here, then I've got the different metals stored, and we're going to have a look at group 1, and then we'll have a look at group 2 just to compare them and get some obvious differences between them. So these group 1 elements we need to have a look at. Now, I've just noticed I've got something missing, so I need to grab a knife so I can cut these things. And let's get started. So what I need is a little knife just so that I can cut the different metals. I've got a clean scalpel there. Right, let's have a look at, first of all, lithium. It's stored under paraffin. I'm just going to move the water out of the way till we're ready for it. And these bottles become double stoppered. So I've got here my lithium, and it's stored in this plastic container. Inside there we've got a glass bottle full of paraffin, and we've got my lithium floating in there. So there's my lithium ready to have a go at. I'm going to move the stopper out of the way. We'll do the same for the sodium. It's stored under liquid paraffin. Again, I'm just going to pour out the vermiculite. It's basically designed to try and protect the items, especially in transit. And finally, the most reactive of the three that I've got, potassium. You'll see that they have these symbols on them here for being flammable. Just move the camera so we can see it. So they're flammable and they're highly corrosive, as you'll see in a few moments. Right, let's take this one out of its container. And this third one is also double stoppered. Just get rid of all the vermiculite around there. So I don't particularly want to get it in the way of the experiments, although it's a very inert material and it's just used for largely packing purposes. Right. There's our three chemicals we're going to have a look at. Let's move the water out of the way. And now we're ready to start. Now, what I'm going to do before I start this is I'm going to sort out some safety equipment. For doing this, we've got to wear eye protection, so I'm going to put my safety specs on. And it's not nice stuff. If I get it on my hands, it's not doing good. So I'm going to go with nitrile gloves. These will hopefully protect me. That's right. Use this so I don't get any on me. Right. So that's the reasonably well protected. So let's move on and have a look at what we're going to look at. I'm going to bring this a little bit further forward. There's our water. Let's have a look at our lithium. There's our lithium. You can probably just see it floating at the top. It's quite hard to get out. Sometimes I get the students to have a go trying to do this when they're here. It's not particularly easy to get any of these out. Today is not being any exception. And what I am going to do is I'm just going to try and spear one with the scalpel. And it's quite dangerous. I'm just going to leave it on there just in case. Right, here is our lithium. What you can't tell from the video is how light this is. But it basically feels no different here than lifting up the faucets by themselves. It doesn't feel to be any difference. Let's just wipe a little bit of oil off. Right. What we're going to do is cut off a little bit of this. So Paul's just going to try and zoom in here so you can see. As I cut this off, and it's quite hard to cut. And I peel it back, you can see the shininess of the lithium and this quite quickly starts to change colour. This is reacting not just with the oxygen in the air, but it in fact also reacts with nitrogen in the air. Right. I'm going to now put that back in the bottle because it's dangerous and I don't want to get any water anywhere near it. So there we are. My lithium. Got a small bit here. What I'm going to do is I'm going to cut this in half. And then we've got two bits we can have a quick play with. Right, so here we go. We're going to put it in some water. So Paul's just going to adjust the camera so you can see it in the water. And lithium. Are we ready? 3, 2, 1, go. And it fizzes quite well. There is quite a little stench here of a gas being given off. And that gas is going to be hydrogen. Excuse me. Right, here we go. Let's try it again. And there's our little reaction of lithium in the water. I'm going to use the same water for the next experiment. It's not going to matter too much. Now, this time we're going to have a look at the coffee due to the fumes that have given off. Right, we've got sodium metal this time. The sodium is heavier than water and oil, so it sinks to the bottom, and we'll pull out a small piece of sodium here. It's quite white. This is where it has actually reacted, and I'm going to cut off a small corner. And you can see that as soon as I cut this, the surface colour is changing as it's reacting with the air, and it's losing that immediate lustre that it had. Notice it was easier for me to cut. It's softer to cut. And this stuff I'm now going to put it back. These forceps aren't the best ones to use. We'll just put that back. Inside there, it's safely stored now. Under the oil, and I'll put it on. Right, so we have a small piece of sodium here. I'm going to cut this into 3. So I'm going to show you this little experiment. I'm going to put that over there for the time being. I find that sodium is quite reactive, so we'll just take a small bit of that, just half of that, and we'll put that in the water and have a look at it. So. Small piece of sodium. You ready? Here we go. It's melted, it's formed a ball, and it's moving around on the surface. Now some people think it's got a slower reaction than the lithium, And in some ways it has, because it's got hot, it's melted, it's formed a sphere. This sphere is almost resting on the water, and as it's resting on the water, it's resting on hydrogen. And it's quite reactive. But because there's so little surface area in contact with water, it's hard to see. It's sort of that fast. Right, take a bit, and this time I'm going to try and do. So I'm going to see if I can show you this hydrogen presence. There it goes. And what I'm going to do is I'm going to see if I can light hydrogen. Not easy. I'll try it again. Sometimes you get it really nice. There we are. You can see it for a moment. You can see the yellow of the flame. And then there was hot hydrogen. Going. And why not? I've got one piece. Put that one in there as well. Right. I've got my little piece of. Right. Let's see what we do now. And we'll meet some potassium metal. The most reactive of the three, and as we'll see, it's softer than either of the other two. Just going to wipe my blade. I don't really want to contaminate it. And let's see if I can pick up a piece of potassium. And the answer is not that way round. No. Let's go for a small piece. There we go. A small piece of potassium. Now let's have a look at how well this cuts. Quite a thin piece. I'm not sure that that's going to work as well. Let's try a bigger piece. I'll try to show you it cutting. There we are. Just try and show you what it's like as I slice off a slice and pulls looking in as we go. Let's take a piece off. And there you can see come off, and it changes colour very quickly. And this sort of silver surface disappears nearly immediately. Potassium more dangerous than the other ones. So we'll put it back in there. I've got a couple of bits to play with. Those two bits can go back in. Right. So here is my piece of potassium. I've got one piece which I want to save for later. So I'm going to put that over my piece of sodium. Cut this in two, and we'll try this one in the water and see what happens. So let's carefully put that away. And now we're ready. We can see already this water has become quite cloudy. We've got a mixture of lithium and sodium hydroxide in here. Let's see what happens if we put in a small piece of potassium. And it lights straight away. Catches fire. More reactive. Here we go. And it tends to finish with a little explosion. Just say one more bit. Gets hot enough to actually ignite the hydrogen juice. I've got some bits of potassium and sodium and lithium on here. Right. Now over here I've got a piece of potassium and a piece of sodium. They've sort of oxidised on left of them. And I'm going to cut half of that off. And I'm going to take about, I really want about the same amount of each. So I'll leave those two bits to the side. And I've got here a piece of sodium and a piece of potassium. Now, if I start cutting these, I want to try and keep them closer together. Just try and put them together. And I'm going to try and swash them together. And as I'm swashing them together, you might see that it's starting to form a liquid. Now this is quite a potentially nasty liquid, because this is liquid and potassium and sodium joined together. It's an alloy, and it's a liquid at room temperature, you see. And what I'm going to do is just chuck a little of that in the water. And much more reactive. We see the bright colour of the sodium and the potassium. The potassium will come to the reaction go, and the sodium is driving colour. You're not seeing the colour of the potassium because it's masked by the sodium. Here we go again. So we've got a little bit of sodium potassium there, and I'm just spreading it out. Right, so there are two metals, sodium and potassium. Mixing them again. Got two small bits. Largely here it's more sodium than potassium. Now, what do we do with this piece of paper once I've finished with it? Well, it's actually quite dangerous, this. And what I ought to do with this, I suppose, is just rinse it under some water. So I'm just going to clean the faucet as well. And Paul's going to focus on the sink. And I'm just going to dump this into the sink to show you why you shouldn't throw this away in the sink. Just point that way. I need to cover it. Right, so I've got my sink. My sink has to be wet. And let's just throw this away casually. And as you see, it immediately catches fire. And the safest thing I can do with this is literally dousing in a lot of water. And I can now make it possible to breathe by opening the window. So there is our piece of paper now, quite safe. I'm going to throw that away, and we're going to have a look at a couple more reactions. Now this is called the alkali metals, and this solution is quite alkaline. And if I put some universal indicator in there, it will turn quite blue. Had I been more organised, I'd have had that out, but I didn't. So I won't. I remember most things. And I'm just going to chuck this down the sink. Let's take the water down there. Let's clean this one out, and then we'll repeat the experiment. This time, I want to have a look at, rather than the group 1 metals, have a look at a couple of group 2 metals. Just to compare the reactivity in the periodic table. So here I've got some calcium. And calcium's this quite hard metal. If I try and cut this with the knife, well, I'm just going to do it. It's just too hard to cut. So I'll leave a couple of pieces out, put the lid on. And let's chuck this in the water. And you'll see it's nothing like as reactive as the group 1 metals. It is going to react. And there we are, start to get some bubbles formed. And we might be able to prove their hydrogen. And my piece of calcium is going in there. And it's starting to go cloudy because it's reacting with water. It's now starting to float on the hydrogen. Hear it? And we've got that one. Was just about staying on fire. We're getting it very cloudy. This is calcium hydroxide formed, which you probably know as lime water. Okay, so that one is quite reactive, but not as reactive as the group 1. If I just get out a beaker, we'll look at one more. Simple reaction. And here's some water. We're going to look at a piece of magnesium reacting. This is lower in the periodic table than the calcium. So if I put this in water, it's incredibly boring. And basically, it's not doing anything, and it won't react, and it won't get anywhere anytime soon. But we still can show these to be quite reactive. Now, what I'm going to do next is I'm going to try and show you what happens when we burn some of these metals. And what we're going to do is we're going to burn a piece of calcium in a flame. But first, I'm going to burn a piece of magnesium in the flame. You've all probably done the burning of magnesium. Paul's probably going to stand a little bit further back for this. And we're going to put this in the flame, see what happens. And then we'll try it again with the calcium, so you can sort of compare them. I'm going to use this burner rather than a Bunsen because I want to burn and it's going to fall down. So I'm going to leave it aside. So let's try the magnesium first. Right, you ready? Here we go. Paul didn't expect me to move down as much then, sorry. So there is the magnesium burner. We're going to do the same with the calcium. And we're going to see what we can do with this now. Let's see what we can do. We have to heat this one up a little bit more vigorously. Really want to try and get it red hot, and then hopefully there was calcium burning. It takes a lot more welly to get it going, but when it gets going, by gum, is that good. And of course, it sets all the smoke alarms off as well. So there was calcium burning as well as the magnesium. Can we do the same with the alkali metals? Can we burn those? Yes. Do they burn vigorously? Yes. And so vigorously that I'm actually not prepared to do that here. I need a bit more space to try and work. It's going to be more reactive than the calcium, and you can see how good the calcium was to burn there. Right. Okay, so let's now have a look at our results. We can see that our calcium has now finished. We've got a cloudy liquid. That's lime water. The magnesium, well, that's still sitting in here, not reacting, and I can leave that several days for it to do that. And take my gloves off. What I'm going to do is I'm just going to put one hand, take one off, put the glove in there, then take this glove off, and that leaves all the nasty stuff inside. So that's ready to dispose of. Right, I don't do my safety specs anymore. And let's have a look at our results. So let's see what we've managed to find out here. Lithium reacting with water, and we'll also put here cutting it to give some idea. So this was sort of quite hard to cut. We can say whether it floats or not, and the case is that one, yes it is. Quite hard to cut, but I could cut it with a knife. With water, yes, it reacts. It gives us hydrogen, and I could describe this as quite reactive. The sodium cutting, this was more like sort of cutting something like hard cheese. It didn't float. And again, we've got the hydrogen, and this one more reactive. Let's call this one very reactive. Potassium, no, it didn't float. This was more like cutting soft cheese. And again, we got hydrogen given off, very reactive again, and it normally exploded at the end. So taking what we know about these, can we guess about rubidium and cesium? Well, yep, we can try some of those. We can see, in fact, that on these, if I look at their melting point, lithium was a solid. Sodium was a solid, but it did actually melt. We've got potassium, and very hard to tell whether that melted, but again, it was a solid, and we might have just about seen it had melted. Rubidium, well, let's see if we can guess with this one. Yes, it's going to produce hydrogen, and this one tends to explode on contact with water. Cutting, well, in fact, it's going to be very soft, this one. And sometimes it even melts under studio lights. It won't float again. It's getting way too heavy. And the cutting of this one is almost like cutting through sort of something even softer than cheese. Butter might be a better description. Cesium, well, this one, yes, it gives hydrogen again. This one normally explodes before it hits the water. Cutting is usually irrelevant because this one is normally liquid under it's sort of just about the high 20s, low 30s sort of melting point. So this one doesn't float, and cutting is usually irrelevant because a lot of the time with cesium, I find that it's actually turned to liquid. So there are reactions of these. Let's have a look at now to compare that with the group 2 metals. Now, what can we say about the group 2 metals? We looked at 2, magnesium, and we looked at calcium. Well, we burnt them, and magnesium, this one burns with a very white, bright flame, and the calcium is much more of, I would call it, an orange-red flame, as it was sort of illuminating the room. And this one seemed to be even brighter than the magnesium. With water, what happens? Well, the magnesium, well, it didn't react with water really. And this one was slow, and it gave off again hydrogen gas. So we've got the group 2s being less reactive than the group 1 elements. So we've looked at a couple of different groups just to compare them, and we can see that the reactivity of the periodic table is sort of, well, let's have a look. As we go down the group from lithium to sodium to potassium, it's getting more and more reactive. Down to rubidium, very reactive. Cesium, the most reactive metal that we've got. Yeah, now about francium. Well, it isn't actually. There's two reasons why. One, we just can't manage to get enough in the world, because as soon as we make it, it's radioactive. It breaks down into something else. And the other reason it's not as reactive is that it's got all of the extra lanthanide metals in the extra shell. And this tends to make it a little less reactive. So francium, if we had any, won't be as reactive as cesium. Cesium, our most reactive metal. Compare that down to the group 2, and the magnesium burnt but didn't react with water, so really less reactive than the lithium. And the calcium, well, that burnt again really well, but less reactive than lithium. So we can look at these group 2, the alkaline earth metals, and say that they're less reactive than the group 1 metals. If we went down that list, the magnesium, calcium's more reactive, we can predict that strontium will be more reactive than the calcium, and barium again will be more reactive than the strontium. And lastly, we've got radium, and I'm not brave enough to play with that one. It's again highly radioactive and pretty dangerous to play around with. So we've got a whole series of those elements, and some of them are easy to play with, easy to get hold of and work with, and others really are too dangerous to get hold of. Mind you, getting hold of lithium, sodium, potassium is normally fairly restricted. Magnesium, where do we find that? Well, many people find that one in aircraft mixed with aluminium to make strong but very light alloys. Calcium, I'll have to think about that one, where calcium's actually used. And my chemist next to me doesn't know either. So there is the sort of series going through. We've looked then at the alkali metals, their properties. They are all fairly soft with low melting points and low boiling points. They're stored under oil because they're so reactive. They in fact form lots of white compounds, all the chemical compounds you've met of things like sodium chloride, they're white, they're all white. They react violently with water, and there are a few videos up on YouTube of people putting a chunk of sodium in water and it explodes, which is why I only used small amounts. They do burn in air really quite easily, but I'm just not prepared to do that. I'd like to keep my home. They will react with chlorine gas. That one we have to do in a fume cupboard, and I don't have one here, so I'm not going to do that one. So we look at the reactivity. Lithium, sodium's more reactive than lithium. Potassium is more reactive than sodium. Rubidium is more reactive than potassium. And finally, cesium, our most reactive alkali metal. Next time, we'll start having a look at the halogens and what they do and how they react. I'm limited with what I can do here because I don't have a fume cupboard, but we'll have a look and see what they actually do. So I'll see you again on Wednesday. I will see you then. Next lesson. Take care. Bye-bye.